problem. Okay, perfect. Good morning, good afternoon. It depends on where you're joining from. So I'm Dr. Mohammed Jalar, and I'm an associate professor at the Department of Civil and Environmental Engineering, and I'm the moderator of this session. So I wanted to welcome everyone to BTR 7, Western section number 4, which is the safety, risk, and crash analysis. Today, we want to have 6 great presentation, and each presenter will have like 10 to 15 minutes, followed by 5 minutes Q&A. So please feel free to put any questions that you have in the chat box, so we will review it after each presentation. So given this, without further delays, so we're going to jump onto the first presentations. The title is Better Safety Analysis Through Smarter Data, Adding OpenStreetView and Traffic Calibrated LBS Data to Pedestrian Crash Analysis in Lincoln, Nebraska, which is presented by Mr. Mohammed Elia, which is a PhD student and a graduate research assistant in the Department of Civil and Environmental Engineering at the University of Nebraska-Lincoln. He holds bachelor's and master's in civil engineering. So, Mr. Elia, please feel free to share your screen.
Thanks, Dr. Jalar. I'll share my screen. Can you see it?
Yes, perfect.
Can you hear me well?
Yes.
Okay. Thanks again, and hello, everybody. Today, I'll be presenting our research titled Better Safety Analyses Through Smarter Data, Adding OpenStreetView and Traffic Calibrated LBS Data to Pedestrian Crash Analysis in Lincoln, Nebraska. Now, our key motivations for this study are not lost on anyone here. Pedestrians are vulnerable road users. Walking improves health and cuts carbon emissions, so we want to encourage it. We have over 70,000 pedestrians injured yearly. Pedestrians' fatalities now account for 16% of all traffic deaths, which is a 30-year high. Our objectives include using large-scale smart data to enhance the precision of pedestrian crash analysis, develop detailed models to assess crash counts and severity, compare the performance of generalized linear models and machine learning models, and provide data-driven insights to inform and shape effective pedestrian safety policies. Our innovative data sources include Mapillary, which is a free street-level imagery service that includes computer vision detection of up to 152 street objects, including signals, crosswalks, and streetlights, and so on. We also have Streetlight, which provides location-based service indicators for vehicle, pedestrian, and bike volumes that we later calibrated into real-world volumes. If you're interested in the calibration work, it'll be presented tomorrow at BTR and the 13th Western track. This is an illustration of the calibration work, which shows that we used EPA of streetlight data into real-world volumes. The prediction accuracy of the model on the test data was as high as 95%, and the paper proved that contextual variables obtained from EPA had a major role in boosting the predictive accuracy of the model. Now, moving on to Mapillary. Mapillary's computer vision model uses semantic segmentation to assign labels to every pixel in the street-level imagery. This is the foundation of their object detection capabilities. Mapillary recognizes over 150 object classes, including driveways, potholes, motorcycles, and more. We use the Mapillary API to query, download, and process detections into our geographic units. This is a list of the Mapillary detections, which can be found on their website. Now for our geographic and analytical framework. The study area is Lincoln, Nebraska. We divided this study area into 50 by 50 meter square grid. We landed on the square size through an iterative procedure, where it turned out that this square size offers representative squares in terms of how much data they offer, but at the same time, they had minor overlapping with other surrounding squares in terms of detections. Now that we divided the city into equal squares, how do we decide which squares are to be included? We tried to balance sample size and relevant data criteria. When we spatially joined the image detections and tested random samples, we noticed that squares that had less than 7 images did not really provide enough information to be considered proper observation points. So it was decided that only squares with 7 or more images are eligible geographic units. For modeling, our key variables include calibrated pedestrian and vehicle volumes. Those are continuous variables. We also have mapillary detections. And since we expect the same detection to appear in multiple images per square, we treated detections as indicator variables, as in 0 versus 1. Our target variable is crash count for the crash count model, and the maximum crash severity noticed or observed in a square for the severity model. This is an illustration of how the different data sets were assigned to our geographic units to form individual observations. Now, the two maps here validate the granular approach that's been espoused in this study. They show crash counts scaled exponentially by severity, meaning when green indicating low count and severity, and red representing high count and severity squares. The left map shows the traffic signal detections largely coincide with high count and severity zones, where in the right map, we have arrow markings, and they are often found either away from or on the peripheries of these zones. This aligns with our understanding of crash patterns, as signals where crossing are located where crossing activity happens, whereas the arrow markers are usually located upstream from crossing locations, and so they're expected to be a little bit away from where the red zones are located. Now, our crash count data analysis showed approximately 90% of eligible squares had 0 crashes, which is not expected. They also showed that crash occurrences in the remaining 10% ranged from 1 to 8 crashes, which offers reasonable variability. For generalized linear models, we tried Poisson, negative binomial, and zero-inflated negative binomial. To avoid dealing with over 150 variables, we employed elastic net regularization technique to help select variables, reduce complexity, and avoid overfitting. For machine learning, we use two approaches that are usually immune to overfitting. Those are random forest model and then gradient boosting machines. The table here shows a summary of the pros and cons of each model based on the analysis results. Our data showed over dispersion, so that kind of means Poisson was not a valid choice. Negative binomial was the best in terms of fit and logical variable significance. Zero-inflated negative binomial, although it's ostensibly better fitting for our data, it showed that there were important variables like pedestrian volumes that were not included in the model. They turned out to be insignificant. Machine learning models were superior in performance. Gradient boosting machines edged slightly in terms of performance, but random forests had better variables contributing to the predictive accuracy of the model. You can see here how random forests employed perceptibly more important and informative variables like pedestrian and vehicle volumes, which leads to the question, is predictive power really worth the trade-off here? I don't think so. Now, moving on to the next model, which is the crash severity model. Here is a distribution of the maximum severity per square and the network of eligible squares. We first attempted an ordered logit model, but severe class imbalance exhibited by the data hindered its ability to predict rare and severe cases. Minor injuries dominate the crash data here, while fatalities and serious injuries are rare. making accurate predictions for severe cases difficult. And honestly, there isn't much to say in favor of a model that underperforms in terms of predicting fatalities. So our solution was to transition to a weighted random forest model, which assigned higher weights to underrepresented classes to improve prediction accuracy. The impact of weighted random forest was noticeable in enhancing sensitivity to severe crashes, providing more reliable safety insights. Just to give you an idea of the role of weighting here, for fatality class, which had a tenuous support of only 15 observations out of a total of 663, we achieved a precision score of 88% and a recall score of 100%. I'll explain both terms in the next slide. So here it looks, precision is true positive divided by the total of true positives and false positives, where recall is true positive divided by the total of true positives and false negatives. Since both are important and we want both of them to be high, that leads us to the F1 score, which is a combination of both. The most significant gain of the weighting is not the precision scores, but rather the fact that we significantly improved the model's ability to accurately predict the less common classes, which include fatalities. The results of the severity model show that weighting improved the performance, and most important variables made sense here. By taking a look at the most important the five most important variables here, we have vehicle traffic and pedestrian traffic. Those are linked to exposure, which makes sense that they appear right at the top. We also have utility poles and support, which usually is attributable to visual obstacles and impact hazards. We also have store signs, which indicate increased pedestrian and vehicle activity near commercial areas. And finally, advertisement signs, which indicates potential driver distraction. Now, you may have been wondering if we took into account the fact that there might be a temporal mismatch between crashes, detections, and volumes. Our crash data was from the period between 2010 and 2020, where our streetlight and mapillary datasets are relatively recent. This mismatch risked overstating effects of features that are not present when crashes occurred. We tried the year dummies at the beginning, but they failed, likely due to the sparse data and collinearity. Our solution was to group years into three broad periods. Number one, post-recession, that's 2011 to 2014. Number two, pre-pandemic, which is 2015 to 2019. And finally, pandemic, which is 2020 to 2021. Our approach resulted in an improved model fit and reduced error, but not anywhere close to invalidating the results. You could think of this as good news because the paper is trying to pitch a simple and a quick granular method to enhance crash analysis. And going through layers of filtration of data and modeling temporal shifts might not really sound appealing to practitioners. So what do the results really mean from a policy standpoint? In this particular case, the results can be used to inform policy to prioritize certain areas over others, and they also could inform policy to tackle specific infrastructure and design elements to enhance pedestrian safety on our roads. Well, talking about study limitations, number one is the limited mapillary data on minor roads. Selecting squares that had a support of 7 or more images led us to eligible squares that were predominantly from major roads. Also, there's some sort of a scarcity of images on minor roads as far as the mapillary data sets is concerned. There's also the class imbalance in crash data. Honestly, it's better to deal with real data than having to rely on artificial inflation of underrepresented classes. Not saying that not having enough high severity crashes or fatalities is not good. It's just from a data analysis standpoint, we'd rather deal with real data than having to synthesize them. There's also the use of squares, which limits comparisons with traditional approaches. For future research directions, that could include expanding data sources, finding ways to integrate grid-based results with traditional units for actionable interventions, and finally expanding this approach to areas with different built form contexts. Now, finally, a recap. The study here demonstrated the value of Open Street View imagery data and streetlight data in crash modeling using our granular approach. Our models showed alignment with expected crash patterns, and practical applications include identifying high-risk locations and informed policymaking. Well, thank you very much, and I'll leave this on for a while so you can take a screenshot of the QR code if you want to read the full paper.
Perfect.
Thank you.
Thank you so much, Mohammed, for great presentation. So any question for Mr. Align?
You're welcome.
You can actually put it on the chat box, or you can unmute yourself. Any question? So meantime, I can ask Mohammed, I have one question. So in terms of the analysis for pedestrian involved crashes, so did you run a separate analysis for pedestrian crashes that happen at intersections versus non-intersections, or you combine them both?
They were combined. Well, initially we tried that approach, but it turned out that we would end up with very tenuous support if we had to separate intersection-related crashes from mid-block crashes. Because after filtration of the boxes, it turned out that we do not have enough support for both. So answering your question, no, they were combined. They were not separated.
I see. And there's one more question, that did you use any feature reduction method?
Yes. Yes and no. For machine learning models, we relied on random forest models and gradient boosting machines' inherent abilities to reduce multicollinearity and deal with it. But when it comes to the generalized linear models, specifically the negative binomial, which performed well, we relied on ElasticNet, which is a regularization technique that both shrinks the betas and at the same time selects variables to avoid multicollinearity.
Perfect. And
I believe it was mentioned in this class, in this slide, if I'm not mistaken. Yeah, I think, yeah.
Perfect. And the next question is, when are you presenting the traffic calibration results?
It's gonna be tomorrow in track number 13, Western 13.
Awesome. Okay. If there is no more question, again, thank you so much, Mohammed, and then we can actually move on to the next presenter. So thank you again.
Thank you.
Our next presentation's title is The Role of Insurance in Nighttime Hit and Run Crashes, the Geo-Spatial Analysis, which is presented by Ms. Yangfang Su, which is the grad student at the Department of Civil and Environmental Engineering at the University of Alabama. So,
Oh, sorry. So how can I share my screen?
Can you hear us?
Can I share my screen?
Yes, please, go ahead.
Okay.
Awesome. Yeah, if you can just please make a full screen, that's gonna be perfect.
Oh.
We cannot see the main page. Is there any way that you can make it full screen? Right now it's not.
Here is okay, so
Again, it's not a full screen. So it's gonna the slideshow. Maybe you can just, if you go back again. Then maybe you can just present it from the main slide deck, so not the. You just click on the bottom right, so that you can actually. Yeah, there is actually, if you go down, so you see it on the close to the zoom index on the right bottom. So there's a display icon. If you click on it, it's gonna be getting full screen. Yeah, if you go down, so you see, go down, please, on the right. You see that there is a like a scale for the zoom percentage. If you go, no, go down. See that is a 113 at the bottom. So you see that?
This one?
Getting down, please. Yeah, getting down, down. You see that 113%? Go down, please. More down. No, just the let me see. But anyhow, so maybe you can just start it from the slide and then keep it as it is, and then we can, yeah, I think we can go ahead.
Okay, I'm sorry.
No problem.
I'm Yanfang Su from the University of Alabama. So today I will present my research, the role of the instruments in nighttime hit and run crashes, a geospatial analysis. So here's a quick overview of today's presentation. So I will begin by introducing the background, the motivation for the study, and then outline the research objective and methodologies and data, and then the key results, and finally close with the conclusion and the study limitations. So to start, let's clarify what we mean by a hidden run. It occurs when a driver involved in a collision, so whether it with another vehicle, a pedestrian, a cyclist, or even fixed object, which leaves the scene without providing contact information or offering the assistance. So this behavior is especially troubling at night when visibility is low and crash victims may be harder to detect for help. And the hit and run crashes present a critical challenge
Sorry to
for
interrupt. So there is a comment that if you can just please speak louder. So there are a couple comments on.
Oh,
yeah,
oh,
please.
okay. To the public safety and the law enforcement often result in severe consequences for victims and complicating emergency response efforts. According to latest traffic safety facts by the National Highway Traffic Safety Administration, the hit and run crashes result in nearly 6,000 fatalities nationwide for the year of the 2021 and 2022. And these crashes are particularly dangerous for the pedestrian and the cyclist. By focusing the spatial dynamics of the hit and run behavior, this research contributes to more comprehensive understanding of the factors driving these crashes and underscores the importance of the region-specific strategies in addressing this pervasive issue. The objective of this study is to explore the role of the instruments in nighttime hit and run crashes, especially addressing the research questions. The first one, what are the special variations and unobserved heterogeneities in hit and run crashes related to geographic factors? And the second is how is the presence of the auto insurance related to the probability of the driver fleeing the scene after a collision during the night. Considering the driving behavior could be related to the diverse geographic context, the influence of the insurance and other contributing factors on hit and run decisions may vary, especially during the unobserved heterogeneity related to this context. For the methodologies, here I use the three methodologies in this research. The first, logistic regressions models, the commonly used for the dynamic classification, so which is employed in this study to assess factors related to the hit and run crashes. With the hit and run behavior is being to yes or no outcomes. The dynamic logistic models is ideal for this analysis. So the logic model assumes uniform coefficients implying a stable relationship. The second is geographic weighted logistic regressions, which can analyze the binary response factor like the hit and run crashes with the spatial heterogeneity. Unlike the global regressions, so this method performs the local regression at each geographic point. The spatial weights are based on the distance between the observation and the center point, with the closer point having the higher weights. The last is the non-stationary, the stationarity test, which can check if the correlation coefficients changes spatially. So for the data part, we use the georeference crash data from the Pennsylvania Department of the Transportation for the year 2023. So our research focused on the nighttime crashes, and we examined the wide range of the variables, including the incidence, crash severities, and type, the lighting conditions, the road class, road condition, and speed limit, and weather, vehicle, and driver characteristics such as gender, age, and impairment, and whether the crash occurred on a weekend or involved with the vulnerable user like the pedestrian or cyclist. So now to the results. The map shows the spatially varying relationships between the hit and run and the presence of the incidents. So we use the GWR to model the spatial heterogeneities in hit and run behavior. At the state level, we found that the influenced drivers are less likely to flee the scene of the nighttime crash, and when we zoom to the Philadelphia region, uninfluenced driver here are far more likely to flee. So increased risk may be influenced by the localized factors such as the high claims rate or the legal consequences. So this highlight of the value of the spatial models. They uncover the local variations that the traditional model might miss. So the map shows the GWR estimates between the hit and run crashes and the selected factors, the driving under impairment, the fatal crash, set swipe, and the involvement with the pedestrian and the cyclist. The figure A shows the spatial distribution of the relationship between the impaired driving and hit and run crashes. For the center and southern Pennsylvania have the higher positive coefficients, indicating the stronger associations. And figure B shows the relationship between the fatal crash and the hit and runs. Across the date, the coefficients are predominantly positive, especially in the southeast and the western regions. So the figure C highlights the spatial distribution of the set swap crashes related to the hit and runs, and we can see that the coefficients are positive throughout the states, with the very high values in urbanist regions like the Philadelphia, the Pittsburgh, and parts of the northeastern Pennsylvania. And the last figure shows the crashes involving the pedestrians or cyclists, revealing the higher possibilities in western and eastern Pennsylvania, particularly near the Harrisburg and the Philadelphia areas. The marks by the red and orange shading in these regions The coefficients is constantly positive and relatively large, indicating a high association between the bicycle or pedestrian environment and the possibilities of the hidden runs. And in the center, northeastern and part of the western regions, the possibility of the hidden run crashes is lower as the coefficients is smaller but still positive. So for the results, the driving under impoundment and fatal crashes are positively related with the hidden run crashes, with the regional variations unobserved across the state of the Pennsylvania. For the center and the southeastern Pennsylvania shows the high incidence of the hidden run caused by the impairment driving, and the fatal crash-related hidden runs are concerned near the urban centers like the Philadelphia, and which they have the which they need to have the stricter traffic law enforcement to improve the safety. And the side swaps resulting the hidden runs are more frequent in the urban areas, particularly in the western, eastern, and the northeastern regions of the Pennsylvania. And the bicycle pedestrian-related hidden runs are higher in the Harrisburg and Pennsylvania, Philadelphia, which highlighting the needs of the increased the traffic enforcement and the roadside warnings in this area. So the to include, so this study investigated the spatially changes influence of the auto incidents and other factors on nighttime hidden run crashes in the Pennsylvania by applying the GWR approach, and the incidents influence the hidden run behavior, especially at night. And this relationship changes geographically. So the effect is the strongest in the southeastern Pennsylvania, particularly in the urban areas. So the third is the geographic logistic regressions. Is the performance better than the traditional logistic regressions in capture local variations in the crash dynamics. And the first is the multiple factors, including impaired driving, the crash severity, crash type, or others, which can escalate, especially variance impact on the hidden run probabilities. And these patterns emphasizes the needs of the region's specific interventions, such as the target enforcement, the region outreach, and the infrastructure improvements. For the limitations, the data accuracy is a concern. So this analysis only relies on the nighttime hidden run crash data from the handoff just for 1 year. Some crashes may be underreported, especially the minor instances of those occurring in the rural areas. And geocoding errors may be also a concern because it's with the invalid or non-extant locations, which are manually removed, but the rest of the geolocations errors is still remain. And further, this research is released on the police reports, which are often based on the witness or driver accounts, which may lead to the inconsistent or biased reporting. So in this study, a limited number of the independent variables are used for the modeling to reveal the relevance of such hidden run crashes at night, while the GWR model requires a large number of the computational resources. If adding more independent variables to model the results, which will need more computational resources. So that's all my presentations.
Great. Perfect.
Thank you.
Presentation. So any questions for Ms. Su? You can actually put it in the chat box or you can unmute. Oh, there's a question. How much speeding is contributing to fatal death in your area?
So over the 55, yeah, over the 55 is in my data. I filtered this one.
Okay. Perfect. Any more question? Seems there is no more question. Again, thank you so much. And right now we can move to the next presentation. So
Thank you.
yeah, the title of next presentation is What Affects Pedestrian Street Crossing Decisions in Day and Night kind of Scenarios, a case study in Charlottesville, Virginia. So which is presented by Ms. Frida Reda. And actually, she is a final year PhD candidate in civil engineering at the department at the University of Virginia. She's passionate about research relating to roadway safety, vulnerable road user safety, and public transit. Her favorite mode of transportation is walking. So, Ms. Rida, please go ahead and start sharing your screen.
Thank you.
Of course.
Is everyone seeing my screen okay?
Yes, we can see it right now. We can hear well.
Okay, awesome, thank you. Oh, sorry, I think I started the voice.
I think there is a background noise. I'm not sure.
Not quite sure how to remove it. Hopefully that works.
But right now it's good right now.
Okay. No, it's not. Oops.
No, again, it's calm.
Yeah. Does anyone know how to turn off the audio? Because I recorded this for the Google Drive and it's currently present in all of the slides. I could just present from this deck if that's okay with everyone.
Yeah.
Okay,
Yes.
thank you. Sorry for the
Not for
issues. So yeah, I'll be presenting on pedestrian street crossing decisions. For some background, this is similar to what was explained earlier. Pedestrian fatalities have been rising in the US, and this graph is a visualization of how much it continues to increase across the United States. Specifically, nighttime pedestrian fatalities have increased more substantially than what it has during daytime. And when we look at the literature and see what factors affect these pedestrian crashes, they typically involve the roadway environment, such as the pedestrian infrastructure present. It also typically involves road user behavior, which is both driver and pedestrian behavior. And we did a basic literature review where we found that for all of the literature focusing on crossing behavior, it could broadly be divided into two categories. The first being pedestrian route choice, which is how pedestrians determine which route to take to get from one origin to another destination. And we found that the other category is pedestrian crossing behavior, and it is a type of pedestrian route choice, so they are interdependent. However, crossing behavior has been studied somewhat to a lesser extent compared to pedestrian route choice, and factors affecting crossing behavior have typically been related to individual attributes of pedestrians, such as their socio-demographic information, the built environment, the attributes of the trip, such as whether they're going on a work trip or if it's a recreational trip, as well as the traffic conditions. However, the major gap in the literature that we identify is that existing studies typically don't account for time of day variations. That is, they only do it at one time of day, whether that's day or whether that's night. And they often lack the perspective of the pedestrian themselves, often using system-centric measures such as surrogate safety or video data. And overall, modeling crossing behavior has been considered challenging due to the unpredictable nature of pedestrians. Pedestrian route choice and crossing behavior have been found to be dynamic choice processes because most individuals are unlikely to schedule their decisions in advance of a trip. Discrete choice models have also been found to be the most appropriate for modeling crossing behavior in general. So with that in mind, we had two broad objectives going into this research, which the first of which is to understand how pedestrian street crossing behavior varies in daytime and nighttime along the same urban corridor using a within subjects approach, and then to develop an overall data collection framework and analysis methodology using mobile eye tracking technology for user-centric pedestrian data. So to do this, we designed an experiment which is located along Water Street in Charlottesville, Virginia. It is a very pedestrian-heavy corridor with a lot of pedestrian crashes. The data collection period was back in 2023, November and December. And as mentioned earlier, we did this experiment in both daytime and nighttime using the same participants. For the sensors used, the two major ones were lux meters, which we used to measure light intensities along the corridor, especially at nighttime, and eye tracking glasses, specifically the Tobii Pro glasses, which were worn by every participant so that we could get a we could get the video data from the pedestrian's perspective and see what they're looking at as they walk. For the exact details of the experiment, the way it worked was that all participants were asked to start walking from this point all along the sidewalks of this side, which is the north side, and all participants were asked to make a mandatory crossing over to this side at this intersection, after which they were given the option to cross back at any of the points that they would normally cross back and just meet us back at this point. So there were 5 intersections during this corridor, and each of them had slightly unique characteristics. The first one was a high visibility crosswalk with a stop sign. The 5th intersection was also the same. I-2, which is the second intersection, did not have a high visibility crosswalk. It just had a decorative paved crosswalk. And the 3rd intersection is the only intersection in this route that had a pedestrian push button as well as a traffic signal. And overall, during the experiment, before each participants came in, they were asked to fill out a survey, which we collected their sociodemographic information from. They wore and calibrated the eye tracking glasses and got familiar with the route. During the experiment, participants did this experiment twice, once during the day and once during night, in a mostly randomized order. And after the experiment, they did another survey where we asked for their perceived safety data. And we asked to identify locations where they felt unsafe. The definition of unsafe was left up to the discretion of the participants themselves. So it was mostly a broad definition. Coming to the data description that we collected from the pre-walk survey, we collected their sociodemographic information and used this later on in the model. We also used eye tracking glasses from which we could calculate their horizontal gaze variability, which is essentially how fast your eyes move from left to right when you're scanning your environment. And the literature has typically used this as a measure of how much situation awareness a pedestrian has. And we also had head movement variability, which is similar, and it's how much you're moving your head left to right when you're walking. And then, as mentioned earlier, we measured the light intensity and the light values, and the post-walk survey gave us indicator variables relating to whether or not they felt unsafe before crossing a particular intersection. We had a relatively small sample size, which I forgot to mention earlier. It was about 63 participants. So we tried to be as thorough as possible and did some exploratory analysis with descriptive statistics and some explanatory analysis with a binary probit model. Coming to the analysis results, firstly, looking at the crossing behavior for both daytime and nighttime, it's not very clear in this graph, but most of the participants chose to cross at the 3rd intersection, which was the only signalized intersection, which you can see with the width of the arrow over here. Most participants did choose to cross within the first 3 intersections in both day and night scenarios, but it's interesting to observe that although most people chose to cross the 3rd one, there was a slight dip in the number of people who preferred this intersection at nighttime. And we also asked them to identify the reason for why they were choosing to cross at the location they were crossing. And in both cases, the presence of the traffic signal was the most influencing factor, but this percentage of people saying this as the reason does decrease at nighttime. Whereas we can also see that the presence of lighting, whether that's better lighting on one side, was an important factor in a lot of people's decisions at nighttime. Next, we also looked at the gender and age effects within the crossing decisions, and we found that overall, during the day, both almost half of the male and half of the female participants were choosing to cross at I-3, the signalized intersection, but at nighttime, a lot of the males decided not to cross at I-3 anymore, and this kind of reflects their risk-taking behavior that we've typically seen in literature. And when we look at it by age, we had a very diverse age range group where we had participants up until the age of, I think, 89. So we did look at these different age groups and how they chose to cross across the different intersections. And we found that the elderly age groups were more likely to cross at the third signalized intersection. That is, they would walk further to get to that point to cross over there rather than cross at the first two intersections. And overall, we see that pedestrians are exhibiting some distinct crossing behavior in the day compared to the night. Particularly at nighttime, we don't have time to really get into this in this presentation, but a lot of participants who reported feeling unsafe were showing tendencies to cross over sooner. Coming to the head movement and gaze variability analysis, we found that overall at each of the 5 intersections, the head movement was higher during the day than it was at night. We only measured this 10 seconds prior to them crossing at each of the intersection, and we found that head movement was higher during the day. This aligns with previous literature because traffic is usually higher during the day, and so when they're about to cross, they're moving their heads more to look around for traffic. And at night, we find that it's the opposite for gaze variability, where it's higher at nighttime than it was during daytime. And literature has indicated that gaze variability, that is their eye movements, are related to their situation awareness. So it's possible that they are more cautious about their surroundings at nighttime, leading to the higher median values. Next, we did a binary probit model for each of the first 3 intersections, where the dependent variable was whether or not they would cross at this intersection or not. And so we did this for each of the first 3 intersections specifically because these are the 3 intersections which had the most people. We chose not to look at the 4th and 5th intersections because they had very few participants crossing over there, as well as the mid-block locations. Overall, we find that for I-1, the very first intersection, both during the day and night, if a participant indicated that they were feeling unsafe, they were more likely to cross over immediately. Higher income individuals were also more likely to cross over during the daytime, and we believe it's because the north side of the route had a lot of shopping attractions and restaurants, and literature has indicated these are attractors that can cause people to switch their routes. It was also noted that people who regularly reported taking the bus to this study area were also likely to cross over at this point, and we believe it's because there is a bus stop on the north side, which people who take the bus are more familiar with and may want to stick to that side. For I-2, which was the decorative paved crosswalk and the only crosswalk without a high visibility crosswalk, only intersection, we noticed that people that are older or people who regularly drive through the area were less likely to choose to cross here. And it's interesting because people who drive through here have probably noticed that it's hard to see a pedestrian entering the road. And so having that driver's perspective, they refused or were less likely to cross at this point. And for the signalized intersection where most people crossed, we found that males were less likely to cross, as we saw in the exploratory analysis at nighttime. Some educational degrees did play some influence in these decisions, and people who reported regularly walking for recreation were also more likely to choose to cross here during the daytime. Finally, the conclusions or overall takeaways, we noticed that perceived safety may influence crossing decisions at nighttime. Horizontal gaze variability increased at night, and this may indicate higher situation awareness or cautiousness of pedestrians at night. Pedestrian infrastructure, specifically signalized intersection and push button, were most preferred in both daytime and nighttime. However, the safety benefits of these infrastructures may not be fully realized without additional features like roadway lighting at nighttime. There were a lot of limitations with this study, specifically the relatively small sample size. However, we believe that this type of study typically has a very small sample size, and compared to the existing literature, I think we had a higher than average sample size for the study. We were only able to consider pedestrian-specific static variables for this model, but we have been working on another paper where we can use more variables. And unfortunately, we couldn't include mid-block location crossers, and for I-4 and I-5, we also could not include traffic data because we only had the perspective of the pedestrians and not any external cameras for this study. That is all I have. Thank you.
Perfect. Great presentation. Thanks. And yeah, please let me know if you have any questions. And also there are a couple of questions in chat box that I'm gonna read for you. So the first question said that whatever be the pedestrian behaviors in crossing the street, he will definitely cross the street in diagonal manner. So in line with that, can we design a staggered pedestrian crossing better to increase the length of the zebra from 3 meters to 5 meters?
That's an interesting question. I'm not entirely sure if that's related to this specific study, so I can't answer that confidently. I'm sorry.
No, that's fine. And the second question is, presumably participant took part alone in turn and not as a group. That's the first. And then were there any members of the public, not participants, present on the street during testing?
So yes, they did participate on their individually. They didn't participate as a group. And there were other people present on the roads when they were crossing. So we did ask them whether the presence of someone else crossing at a certain intersection was influencing their choice. And very few people did say that once they approached an intersection and they saw someone crossing, that kind of motivated them to cross over to the other side.
Perfect. And next question is, unsafe means feeling unsafe from traffic or from other factors such as crime?
That's another interesting question. So we did leave the definition up to the participants themselves, but once we analyzed the data, we noticed that it was a combination of both. During the daytime, it was more related to traffic because there was a lot more vehicles during the day, but at night, it was more related to crime and just feeling unsafe overall.
Awesome. And the next question is, how was the time variation for daytime, all equal or depend on the peak time and non-peak by volume?
So we didn't exactly account for the traffic volume variations, if that is the peak you're referring to. I think we collected data from 9 a.m. to 5 p.m., basically only daylight hours, and then once it got fully dark, we resumed the nighttime data collection, but it didn't really vary with traffic. We only collected during weekdays, if that makes a difference.
Perfect. And for all actually participants that ask question, if there's any follow-up question, please chime in. And if there's any more questions, so we can take it now. Any more questions? If not, we can leave. Yeah, thank you so much. And we can jump to the next presentation then.
Sorry, could I ask? I just want to ask one more question. I think, I mean, I know not everyone wants to speak, but I think it's nice when people ask their questions. The question I want to ask is, it's a very interesting study. You know, it's very labor intensive to do these studies where you're actually talking to individual people making decisions in the real world. I just want to ask, what would you, if you could do it over, what would you do differently?
Oh, thank you. That's a great question. I think so this study was rather simple in terms of the model used, but we are currently using more dynamic variables. And I think what we're noticing is that we could have measured the light intensity variables a little more carefully because we only measured it at, I think, 16 points along the route. and it's not quite capturing the pedestrian experience because from the answers of the survey, it seems like the lighting played a role in their decisions and they wanted to be in well-lit areas, but we're not able to capture that as much in the model. So maybe some other way of getting those light intensity variables would have been great for if I were to do this over.
And then there is, I believe there's a follow-up question. How was the light intensity measured?
So we used an instrument called a lux meter, which you just calibrate and you measure at discrete points along the route. And we measured that every time a participant did the route and got the average.
Awesome. Perfect. Any more questions? Okay, if not, again, thank you so much, Ms. Raida. Great presentation. So I think we can move on to the next presentations, which title is Move Over or Slow Down, Simulation-Based Evaluation of the Safety Impact of Motorist Actions in Compliance with Move Over Laws, which is presented by Mr. Jai Kong, who is the second-year PhD student at the University of Alabama. His research interests include traffic simulations and data analysis. The floor is yours, Mr. Kong.
Hello, I would like to share my screen.
Yes, please.
Yeah, I just hope my screen content can be shown
Yes.
properly.
Yes, we can
Thank
see
you.
and hear well. Yes, please.
Hello, everyone. My name is Jia Kong, and I'm a second-year PhD student in the University of Alabama. Today, I would like to share my recent study. The name of the study is Move Over, Slow Down, a simulation-based evaluation of the safety impact of motorist actions in compliance with move over laws. So first, I would like to introduce the term of first responders, but I'm not sure if the word first responder is available in all countries around the world, but at least in the United States, they will call first responders. We can also call them emergency vehicles. So basically, those emergency vehicles include a bunch of different types of vehicles on the road, including police cars, ambulance, tow trucks, and those workers fixing the road facility or traffic facility cars. So according to existing study, those roadside responders, so first, they are essential to maintain the safety and efficiency of our transportation systems. However, despite their crucial roles, they face significant risks when performing their duties on roads or roadsides. And another study shows, starting from 1999 till recent years, for almost every year, there are more than 10 police officers stuck by vehicles and while doing their duties besides the roads, which shows the dangerous situations of them. So in the next two slides, I will show two videos describing how dangerous of those first responders working situations are.
Get over, people! Gee!
So the first video comes from a tow truck driver, and he's towing the truck besides a highway road. As we can see, he needs to observe those upcoming vehicles very carefully till he find a good chance to walk to his tow truck and begin his other tasks of towing the vehicle.
Okay. Yeah, I'm gonna get off this deck. Good luck. They haven't done it for me. Go get him. Go get him.
Yeah, the second video shows a police officer is quickly running to his police car while concentrating on those upcoming vehicles. As we can see, there was 150 driving on the adjacent lane very close to him and with a very high speed. So until those upcoming vehicles are empty and the road is safe, then the police officer can run to his car and begin his next job. So I just would like to quickly introduce the move over law, which is implemented in all the states or regions in the United States. So basically, in the United States, the move over law is created to protect the safety of those first responders, or we say the emergency vehicles. It is required that when a driver is driving on the road, we are supposing is right-hand driving, and when another emergency car is walking on the shoulder of the road with flashlights on, and for that vehicle approaching to the emergency car, it is required that the driver has two choices. One choice is to move over to the other lane before reaching to the emergency vehicle, and another option is to slow down to a specific speed when passing through the emergency car. So in different states, there are different requirements for how slow you should be when approaching the emergency car if you choose to not moving over to the other lane. So for example, in Indiana state, it is required to reduce 20 miles per hour below the speed limit of that road. For example, if it is a typical highway in the United States with speed limit of 70 miles per hour, then the vehicle, if he or she choose to slow down instead of moving over, then it is required to down the speed below 50 miles per hour. And in other states, it's usually required to down the speed between 15 to 20 below the speed limit of that road. So in this study, we actually want to design a simulation that analyze those factors that affects the feasibility of being in compliance with the move law. So basically, in this study, we do not discuss those psychology reasons for not obeying the move law. That is to say, we don't consider those drivers that ignore the law or playing mobile phones or other situations. We only focus on those special situations that even if a driver is driving very, very carefully and highly concentrate on all the factors, then he also have the chance to fail on obeying the law. That is to say, the vehicle when he or she drives past the emergency car, the speed is higher than the minimum requirement. So the workflow of this study is to design a simulation. That the simulation, the key question or the key topic of the simulation is to analyze how to comply with the move over law. So in order to do that, the simulation, the traffic flow simulation, was designed receiving many parameters as inputs, and after adjusting those parameters in some special cases, the simulation will have the chance to get a result that there are at least one vehicle not obeying the mover law, then we will define the outcome as a dangerous outcome. Then after collecting those dangerous outcomes with the simulator's running context, we can think of the question conversely. That is to say, as long as we know the dangerous outcomes, if we think reversely, if we can have some corresponding strategies to those dangerous situations, then maybe we can improve the safety of those responders, and maybe those drivers originally they are not obeying the mover law, then they will become compliance with the law. So after analyzing the simulation, so basically the simulation has many parameters in the settings, include the vehicle speed, how many vehicles per lane, and many parameters. But in this study, we are only focusing on three main parameters or three main factors. The first factor is when the driver detects the first responder, what is the speed for the driver to take the remaining actions, include his decision time. Well, for example, in a heavy rain, in a bad weather situation, the distance when detecting the first responder's flashlighting is becoming lower. And the second input parameter is how many vehicles closely following the leading vehicle. Whereas we can see in United States highways, those vehicles usually follow closely together, forming a platoon, or we see they are forming a fleet. Usually there are several vehicles closely following each other. And the third factor is the left lane traffic condition. As the simulation is based on the United States highway, the vehicle, if the vehicle wants to move over to the other lane, then he needs to take care of the left lane's traffic condition, and only if he or she gets enough space to change the lane, then he can successfully do it. So the left lane traffic condition is very important to the simulations running. And the other factors, other parameters adjusting the simulation, but those values are not very crucial to the main topic of the study. So this is the other part of the simulation. That is to say, after deciding the three main parameters of the simulation, we run all the possible combinations of the three parameters values to the simulation and get thousands of running results. Among those results, we can find there are some outcomes with dangerous situation. That is to say, among those vehicles, at least one vehicle is not complying with the move over law. Then based on those dangerous outcomes, we can think reversely, well, why the vehicle violate the move over law. So yeah, I would like to introduce the results and the conclusions of the study. So first, the key factor in this study is the sight distance. That is to say, the distance when the vehicle detects the first responder. So the conclusion would be when the vehicle detects the roadside responder at a short distance due to weather, road condition, etc., we suggest that the vehicle slow down immediately. That is to say, in most cases, the left lane's traffic condition is uncertain, and you have very little space to make a successful move over action. Then in this case, it is better recommended to slow down immediately. Otherwise, the driver may have a high chance to spending time on trying to changing the lane, but eventually fail and even wastes the driver's time more. And the second parameter's conclusion of the platoon length. The platoon length means how many vehicles are closely following the first vehicle driving on the right lane. The conclusion would be when there are several vehicles closely following each other and the leading vehicle detects the roadside responder, it is suggested the vehicle slow down immediately. That is to say, in a highway with uncertain traffic conditions, the first vehicle driving ahead, the driver's decision when facing the first responder is very important, because if the driver tried to move over but eventually failed, it may delay or it may reduce the following vehicle's reaction time, reaction distance, and chance of slowing down as well. So the third parameter is the traffic condition on the left lane. So the conclusion of the simulation would be when the vehicle detects the roadside responder while the left lane traffic is very busy, it is suggested the vehicle slow down immediately. Well, I think this is very easy to understand in our real life, since when we are facing a situation that the left lane of our vehicles has many cars with high speed, then we face the first responder. It is generally recommended to slow down immediately to save time and save space. So the conclusions will be the combination of the three parameters. That is to say, when the driver detects the roadside responder and it is suggested the driver tracks the three conditions of the simulation, not the simulation. The driver tracks the three conditions of the road of the nearby traffic. First is the sight distance, and second is how many vehicles are closely following you on behind, and the third is what is the traffic situation on your left side for you to have a move over action. It is recommended that if one or more of those situations satisfied, then it is suggested to slow down immediately to save time and save space for both you and the vehicles following you. And otherwise, well, because in many states' law, it is generally suggested for the drivers to move over. Then, if the condition not satisfied, then slow down. So, if the condition satisfied in all cases, then it is recommended for the driver to move over to the other lane in order to create space and make a safer working environment for the first responder. Thank you.
Great. Thank you so much, Jai. And I would also like to remind all the presenters to see if they can turn on their cameras so everyone can see them. So that would be awesome. And there are a couple of questions. There is a report that I share with you, Jai, and also there is a questions that in Germany, for example, a warning sign known as warning triangle has to be placed some distance before the emergency conflict locations to inform incoming drivers. Do you have something similar in the USA? So it seems that from the video, it seems this is not a case.
Yeah, thanks for your question. So basically, as my experience in the United States, usually if those police cars are following other vehicles on the roadside to do a traffic check, they will usually not placing such a mark over 150 meters behind the car. And if the situation was those tow trucks or road facility workers, they will usually put such a sign. Let me see the sign again. So yes, so in my in my simulation, I did not consider such a science function because it because in the United States, putting such a sign is, I guess, it's not strictly required by those emergency vehicles. But if we think it as a parameter of the simulation, then yes, it can also be considered as the sight distance when the driver detects the sign or the flashing light of the first responder vehicles.
Okay, thanks. And the next question is this: is this more dangerous in two-way, two-lane rural highways? Do you have any opinion that it's gonna be more dangerous compared to different type of roads?
Well, I'm not sure if the two-lane rural in your definition is the road that only has one upcoming lane and one forthcoming lane, that is to say a road of the right side is the one direction's driving and another lane is another direction's driving. In my simulation, I did not consider this situation because in this situation, usually, if we say strictly obey the law, the choice of the driver got only one, is to slow down, and usually in such case, there might be additional workers guiding you how to slow down to a even lower speed. So in this case, I don't think a move over action is necessary or required for the drivers to make decisions. So in my simulation, a 4-lane highway is considered. A 4-lane highway means 2 lanes for one direction and 2 lanes for the other direction.
Okay, perfect. Is there any more question for John? Seems there's no more question. Again, thank you so much for the great presentation. We can move on to next presenter. So the title of the presentation is, Does the Built Environment Matter in Elementary School Zone Safety and Congestion? Evidence from Collisions, Ticketing, Traffic, and Classification, which is presented by Mr. Matthew Blaine, who is a master's student in civil and environmental engineering at the University of Alberta, specializing in transportation engineering and having completed his bachelor in civil and environmental engineering there in 2023. He has a strong interest in complete street design and sustainability in transportation engineering. Right now, he's researching multimodal design and traffic flow consideration for elementary school zones. Matthew, floor is yours. So yeah, if you can just please share your screen.
Perfect. Is that sharing right?
And turn on your camera if it's possible.
I think I have it all on. Can you hear me all right?
Yes.
Yes.
Okay. Perfect. In that case, I'll get started. Hi, everyone. My name is Matthew Blaine, and I'll be presenting my research today discussing the link between the built environment and school area safety and congestion, as well as the classification of schools according to their built environment. So to start off with, this research is focused on improving safety and congestion for elementary schools in Canada, specifically the city of Edmonton in the province of Alberta. So of the 1,800 people killed in motor vehicle collisions in Canada every year, 25% of them involve vulnerable road users like pedestrians, cyclists, elders, and children. This, of course, highlights the need to conduct research about school area safety, as there's plenty of pedestrians and children walking through these areas every day. Beyond traffic safety itself, over the past 50 years, there's been a steady decline in active transportation to and from school for children, which has also been paired with a relative increase in car travel as the primary mode of transportation for school commuting. This phenomenon is in part responsible for acute congestion and safety issues, as well as a decrease in child physical activity. The City of Edmonton tasked us to try and further understand traffic safety and congestion at Edmonton elementary schools during drop-off and pickup hours, which are notoriously chaotic, as parents often try their best to get in and out as fast as possible from the school area to drop off or pick up students. So these problems have, of course, prompted plenty of research and initiatives seeking to improve the safety of vulnerable road users in school areas. In the City of Edmonton, where this research takes place, some of these programs include the implementation of various traffic calming measures, crosswalk upgrades, and speed reduction programs, as well as the construction of various other pieces of infrastructure. Some of these infrastructure options include dedicated car loading zones on or off-site, and the construction of the citywide active transportation network. Beyond the individual improvements made at each school across the city, the existing infrastructure and built environment around each school also has a big impact on the movement of traffic and safety in school areas. Part of our research tasked by the City of Edmonton was to find out which schools' specific conditions affect safety and congestion at these sites. So this line of questioning led us to discussions on the built environment. This is a very common urban planning concept describing urban infrastructure over a certain area, and it's been successfully applied in the past to the topics of not only active school transportation, but also transportation safety around schools in other Canadian cities. While it makes sense that the immediate infrastructure surrounding a school may affect traffic and safety, the built environment also includes greater neighborhood characteristics, specifically the 3 Ds of design, diversity, and density. While the immediate area around every school in a city will certainly vary from one school to another, there's been successful research in the past that has successfully categorized other pieces of urban infrastructure, such as metro stations, by built environment characteristics. So overall, this prompts us to ask the question, if the built environment can be used to predict school safety and be used to classify other common urban infrastructure, can we do the same and group schools with similar built environments together so that we can find more ways to improve safety around schools? So this brings us to our objectives. Firstly, the regression modeling of existing Edmonton elementary school built environment characteristics to collisions, automated enforcement ticketing, and nearby traffic volumes. While the modeling of collisions in this way has been done in other Canadian cities, it has not been done before in Edmonton and has never included automated enforcement ticketing or traffic volume metrics. The second goal is the classification of Edmonton elementary schools into various typologies by built environment through 2 methods, one a manual analysis of street class and configuration, and secondly a k-means machine learning model. The goal of this objective is to use these typologies in our later research to make the implementation of safety and congestion measures smoother than ever. So getting right into the methodology, here's a general flow chart. From left to right, we first collected a lot of data on safety and congestion metrics, as well as built environment characteristics and socio-demographic characteristics. These went into our dependent and independent variables. Some of our sources include open data that the City of Edmonton collects and shares, and the 2021 Canadian Census. Next, for each of our objectives, we created several regression models to eventually find which built environment variables affect traffic safety and congestion around schools. And we conducted 2 different classification methods, the k-means machine learning model and a manual visual analysis to group Edmonton schools. To save time from showing all of our data tables, I've included the QR code here, which shows our full results and all independent and dependent variables if you're interested. And this will also be available on the final slide. So for the regression modeling, we used negative binomial regression for our collision models. This is because collisions are a rare event and there's a lot of over-dispersion, as was mentioned in the first presentation of today. So we had a 2017 to 2023 collision data set, a total of 7 years, and we split up this data set into 5 different portions, 5 different time periods. 3, 5, and 7 years, and then 3 and 5 year periods, excluding COVID years. So we then continued to split the data again by which traffic volume exposure variables were to be included in the model. We include exposure variables because they invariably affect collisions, and it's meant as an exposure variable. We then split up the data again into injuries and property damage only collisions. Only injuries and property damage only, because we did not see any traffic fatalities around our schools in this time period. The automated enforcement ticketing and traffic volumes, on the other hand, were modeled with simple linear regression, with ticketing including all 7 years of our data set, and volumes including only volumes of minor roads adjacent to every school. For the classification, we went through 2 different methods. Firstly, we had a manual classification of every school based on the immediate surrounding road class and configuration, as seen on the left. Schools were first grouped into subclasses and then into larger general classes containing several similar subclasses. The sample shown here shows the process we used for classifying Kirkness Elementary School. In this case, in the first top left image, we see that it only has one adjacent road, denoted by color as a collector class. We then verify this with Google Maps satellite view and finally put it into a table. And then this, all schools with similar tables as to this one would be grouped into the same subclass. The second classification method we attempted was a machine learning classification, which took 20 of our independent variables focused on the built environments exclusively, and went through several processes to eventually create clustered groups of schools. So this included feature reduction, and then we used a k-means unsupervised machine learning model. To get into the results, of the 20 total collision models we built, the 3-year excluding COVID, so that's 2019, 2022, and 2023 time period had the best results and fit. Split by collision severity, we found that most notably, both built environment and social characteristics of the surrounding area can be linked to collisions for each school. Some of the most interesting parameters that we found include that more arterial roads in the area immediately surrounding a school, as well as the presence of separated on-site car loading, drop-off, and pickup zones increased injury and property damage only collisions. On the other hand, higher proportions of neighborhood area residential land use and local roads were linked to fewer collisions. The social characteristic that we found linked to higher collisions was the proportion of low-income households in the area. And you can also see our fit metrics here and in the full data tables. For our classification results, we were able to, no, one slide too far. For our simple linear regression models, there were far fewer significant built environment variables. But of note was the fact that, again, social variables were again linked to both automated enforcement ticketing and volumes. And again, that the presence of separated car loading zones was linked to higher traffic volumes in the school area, just as it was linked to more collisions. So for our classification results, we were able to manually group 155 Edmonton elementary schools into a total of 5 general classes. That's shown with an example of each general class on the left side of your slide now. There's also one other class where schools that did not fit into the general classes were placed. On the left, we see that each of the sample schools are unique and different from each other based simply from a satellite view, but within each general class, they can be easily linked together. We can see that in Edmonton, most schools fell into the single road category where there was only one school, where the school was adjacent to only one singular road, or the minor corner category where schools are on a corner between at least 2 minor roads, that's collector or local classification. We also have grid style where schools appear in a grid style neighborhood, and arterial corner classes where the school is adjacent to at least one arterial road. And lastly, a collector T intersection where a school is within close proximity to a collector and minor road T intersection. So from our perspective, it's easy to imagine and see how traffic may flow very differently for schools between the various general classes. On the right, you can also see these classes mapped across the city of Edmonton. For anyone who may know Edmonton, we also found that these categories largely followed the general development pattern of the city over the years. So we had more of our grid class schools appear in older parts of the city, while the minor corner, single road, and collector T intersections, those schools appear in various suburban areas, often grouped together. Lastly, for our results, while I won't get into it too much, here are the results of our machine learning classification, which clustered all of our schools into 3 different categories as shown by the graph on the right. The table on the left, on the other hand, shows us what the top 3 defining features were for each cluster, essentially saying what were the biggest determining factors in saying a school was in one cluster versus another. In this case, the purple cluster, the one on the right, was heavily defined by the presence or non-presence of a separated car loading zone. The green cluster at the bottom was most defined by the proportion of single-family homes in the area, and the red cluster on the top left was defined by the presence or non-presence of enhanced crossing measures. Lastly, to conclude it, let's talk about the implications and a little bit about further work that's coming as a result of this research. Always the biggest talking point that has come up is how we interpret the link between collisions and volumes with separated car loading zone presence. Since this research was not a longitudinal study, it's hard to tell if the implementation of separated car loading zones on site cause collisions or are already placed in areas with collisions and high volumes already. So another theory on this is that they may reduce congestion and improve safety immediately after their construction, but they could induce demand in the long term by incentivizing more car pickup and drop off. Furthermore, it's often a complaint of schools in the city of Edmonton that many conflicts happen between vehicles and pedestrians within these separated car loading zones on the school site, and many loading zones within Edmonton may have design flaws. Regardless, this finding does echo previous research, which also shows that separated car loading zones are linked with higher collisions, despite the apparent improvements in efficiency and recommendations for the implementation of them. So this leads us to perhaps recommend caution in calling these the best solution to improving safety and congestion in school areas. For our other 2 big findings, the finding that schools in areas with a higher proportion of low-income households also speaks to the idea that school safety infrastructure should be distributed equitably, and there may be some communities across the city that need them more than others. Lastly, that the more arterial roads surrounding a school also increases collisions is not really a surprise for us, but again, may point officials to find ways to improve school area safety, specifically when arterial roads are present. Key takeaways from our classification show that the machine learning classification was mostly an interesting experiment for us since we had all the data already, and it shows built environment variables can also be used to group schools together. But this is a procedure that needs further expansion in the future before it can be applied anywhere. For manual classification, that we can successfully classify such a large proportion of Edmonton elementary schools into only 5 different general classes based on exclusively the road class and configuration is really interesting to us and interesting to the city as well. On the right, for example, we see 4 different schools chosen from within the minor corner general class. And it's not that hard to imagine how one school's traffic flow may look very similar to another's from within the same class. So between the methods, the manual classification proved more intuitive, and so it'll be used in our future work, where we will see if we can effectively apply countermeasures that work at one school within a class to other schools within that same class. Thank you so much for your time and attention. If you missed the QR code with further results and data tables, I have it here. And if you have any questions, I'm more than happy to answer them. Otherwise, thank you again. I hope you have a nice rest of the conference.
Thank you, Matthew. Great presentation. So yeah, please feel free to chime in with any question, but there are a couple of questions on the chat box. So the first question is, so how are students driven to schools without separated car unloading zones? And do you have an aerial photo of such a school? That's the first question. There's a follow-up question that also, what is the typical size of the schools in the student count?
So for this, I'll answer the second question first. For this study, we looked exclusively at K-6 elementary schools. The primary reason for this was that as soon as we get into junior high, which is grade 7 or higher, the mode share of students traveling to school will shift a lot from grade 6 and below. And the general size of school was anywhere from, I'd say, 150 to 250 students, but they're all within that general range. There's no massive super schools in here. And then to answer the second question here, I've pulled up the classification slide again. The photos here on the bottom left and the bottom right are both schools that do not have separated car loading zones. They're generally probably within the 150 to 200 student range. And when students are driven to school here, parents simply drop them off on the side of the road. The bottom right is probably a better example for it, where it's more visually seen from like an aerial perspective. Since there's curb extensions here that create like visible parking lanes, that is typically the location where students would be dropped off. These are typically denoted by signs saying that there's like a specific loading zone, like a 5-minute loading zone, but sometimes there just isn't, and it's just free parking.
Perfect, thanks. Is there any more question for Matthew? Yeah, these are the only questions on the chat box. So any question? Still have a couple of more minutes, so it seems there is no more question. Again, thank you so much for a great presentation. So right now we can move to the last but not the least presentation, which is titled is Segment Level and Intersection Level Driving Volatility Analysis using Large-Scale Crowdsourced Vehicle Movement Data, which is presented by Mr. Xiao Zhu. Mr. Zhu is a second-year PhD student at the University of Alabama. His current research interests include traffic safety analysis, mobility simulation, and optimization. I'm not sure if Mr. Zhu is on the...
Hello, I'm Mr. Xiao's classmate. Mr. Xiao is busy today and he's
Perfect.
unfortunately unavailable for this meeting, so I will show his slides instead.
Perfect. So then can you just go ahead, please, and share your screen? Perfect.
Hello everyone, I'm Xiao. I'm the second-year PhD student from the University of Alabama. Today, I'm very happy to present our research on segment level and intersection level driving volatility analysis using large-scale vehicle movement data. So here is a brief outline of what I will cover today. We will start with an introduction to the problem, move into our research objective, and then discuss the methodology, present the key results, and finally conclude with implications and the future research directions. So let's start with introduction. So traditionally, traffic safety analysis heavily relies on crash data. While valuable, this approach presents some challenges. First, the crashes are typically rare and random events. This means we often need multiple years of data to gather enough information to yield reliable and statistically significant outcomes. Over such long periods, many factors on our roadways, like traffic conditions or economic context, can change significantly, which introduce what we call unobserved heterogeneity, which makes accurate analysis more difficult. However, we are now living in a big data era. So, with the development of connected vehicles and advanced communication technologies, a huge amount of vehicle movement data is becoming accessible. This presents a significant opportunity. Unlike reactive crash data, vehicle movement data allows us to understand the roadway safety performance in near real time. This enables us to proactively identify the safety issues and implement more timely interventions. The key advantage here is the large volume of data and the ability to gain insights over much shorter temporal intervals, which provides a more dynamic perspective on traffic safety. So the central to our study is the concept of driving volatility. So driving volatility measures the variability of vehicle movements, specifically capturing extreme driving instances. Think of it as a sudden, abrupt change in driving behavior. The example include rapid acceleration or hard acceleration or hard braking at specific locations or areas. So we quantify the location-based driving volatility as the score, the percentage of extreme movements at a given location, as shown by the equation 1 on the slide, is the time of the extreme maneuvers over the total driver time at a location. The equation 2 defines the threshold for identifying this extreme behavior. So let's move to our research objective. So our primary research objective was to conduct a driving volatility analysis using the large-scale connected vehicle movement data. Specifically, we are focusing on both the segment level and intersection level of the roadway network. These objectives addresses some important research gaps. Firstly, while existing study has explored vehicle movement data for safety analysis, so many studies have been limited to individual driver analysis or a few specific sites. So our work aims for city-level comprehensive application using large-scale connected vehicle data. Secondly, although traditional traffic safety analysis often focus on segment and intersection safety, existing driving volatility analysis haven't directly linked the volatility scores to historical crash frequencies at these specific locations, which may limit their practical insights for safety implementations. So our research aimed to bridge these gaps. So let's move on to our methodology part. So first, to calculate the location-based volatility, we developed a comprehensive framework, which you can see from the right-hand side. So we are focusing on the Tuscaloosa, Alabama. You can see from the left-hand side, the road network was extracted from OpenStreetMap, and we identify 167 signalized and over 2,000 unsignalized intersections and the thousands of road segments in the study area. So for our analysis, due to the large data size, we have over 90 million driving records during 1 month period. So we apply some efficient spatial matching technique. We use the K-tree algorithm to match the driving vectors to intersections. And then you apply the R-tree algorithm for matching vectors to road segments. This allows us to accurately count those extreme driving behaviors at each specific location. So with our calculated volatility scores, we then move to the modeling part. So our central research questions are, could location-specific driving volatility significantly influence traffic safety? Would including volatility significantly improve our model's ability to explain safety outcomes? And finally, could it serve as a useful measure when crash data is not available? So given that our crash data was highly skewed with many locations having 0 crashes. As you can see in the histogram on slide, we employ a zero inflated negative binomial model. This model is ideal for count data with an excess of zeros. And we developed 2 zero inflated models, one with and without drivability. And we want to compare the performance to show the predictive improvement by driving volatility. So additionally, we also apply fit an ordinary least square models with driving volatility as dependent variables and try to explore these contributing factors and predictive utility. So now let's explore our key findings from our results. The highest volatility was found on city highways with unsignalized left turn lanes. This layout often prompts drivers to perform extreme driving behaviors, which might significantly change their speed and acceleration or deceleration. So for our modeling results, the model results provide some strong evidence for the value of incorporating driving volatility. The zero inflated negative binomial models, which included driving volatility, consistently yield higher R-squared values. Specifically, adding driving volatility improves the R-squared values by over 200% at the segment levels, which demonstrate a significant contribution to understanding roadway safety performance. And also our findings show that driving volatility is positively correlated with crash frequencies at both segment and intersection levels, which meaning higher volatility leads to more crashes. We also found that signalized intersections are positively associated with crash frequency, and segments bounded by signalized intersection also experience higher crash frequencies. And also I want to mention that while volatility is statistically significant at a segment level, however, its significance is less consistent at intersection level. This suggests that volatility is a stronger predictor at the segment level, where driving behavior is generally more stable and less influenced by the dynamic. And lastly, our OLS models, which we use the volatility as the dependent variables. The results also confirm the robustness of driving volatility as an indicator of crash risks. Since those model results, the coefficients were generally consistent with the findings from the zero inflated negative binomial model. So to wrap up, let's look at the conclusion and future work. So in conclusion, our key findings is that a positive relationship exists between driving volatility and crash frequency at both intersection and road segments, with a stronger predictive value observed at the segment level. This study contributes by demonstrating the utility of large-scale vehicle movement data for driving volatility analysis, highlighting its potential as a valuable supplement to traditional. So looking ahead, there are several
Sorry, I mistouched the key. I will
Our key
replay.
findings is that a positive relationship exists between driving volatility and crash frequency at both intersection and road segments, with a stronger predictive value observed at the segment level. This study contributes by demonstrating the utility of large-scale vehicle movement data for driving volatility analysis, highlighting its potential as a valuable supplement to traditional crash data. The implications are clear. We can move towards a more data-driven, proactive approach to traffic safety, improving the efficiency of interventions and ultimately supporting safer and more resilient transportation networks. So looking ahead, there are several future research directions. So it's good to incorporate spatial relationships among locations for a more comprehensive understanding of driving volatility patterns. Also, as more high quality data becomes available, it's better to include additional variables and test more advanced models. Finally, as we talked before, the volatility is not statistically significant at the intersection level, so more targeted research is essential to fully understand and address the inherent complexity of intersection in safety analysis. Thank you. Any questions?
Thank you for the presentation. So there are a couple of questions. I'm not sure if you can take the question or we need to collect those questions and then send to Ms. Yu since he was not able to make it today.
I'm happy to answer one of the questions.
Perfect. The first question is, I'm sure you mentioned this already, but who was your vehicle location vendor for this study?
So vehicle location, I guess the vehicle location vendor you mentioned is the vehicle trajectory data we used in our study. So basically the vehicle trajectory data comes from a local company in Tuscaloosa, Alabama state, a local company which provides several, I guess there are at least tens of vehicles daily trajectory, and sampling with 1, 2, 3 seconds. So basically, it is a full logging of the trajectory of those vehicles.
Okay, perfect. Any more question? If not, again,
Yeah,
so
so sorry, just one more question. And of course, I'd love other people to ask questions too, but volatility, you have to pick a threshold. So I'm wondering, how did you determine, did you do some kind of preliminary analysis to figure out what your threshold is for a volatile event?
did you hear the question?
Yeah, please give me just a few seconds.
Sure. And also, meantime, there are some instructions for the next session. So there's a links for each session. So we should start almost in 4 or 5 more minutes. So
Yeah, happy to answer this question. So in our study, I don't know if this figure is shown in the slide, but we are using mean value plus standard deviation and mean value minus standard deviation to determine the thresholds.
So, Lloyd, is there any follow-up questions, or are you good? I think we should be. Oh, is it great? Sorry. So it seems that we are sharing the same link for the next session. Perfect. So again, I wanted to thank all presenters for the great presentation today, and thank you all for the participant as well. And I hope you have a great rest of the day.